Now let's talk about electric potential energy. Now I want to caution you, this unit is confusing. I'm just going to be honest. A lot of the words are very similar and it can get very confusing. Now, you're going to know you're doing an electric potential energy problem because you're going to see the word energy as opposed to electric potential. Now, you remember the formulas. If you have a uniform field, then the change in potential energy when you're moving in that field is minus QED. Q is your charge, E is your electric field, and your D is your distance covered. Remember this negative sign. It shows that potential energy is lost, and make sure you keep the sign of the charge. So a positive charge is positive, a negative charge is negative. And remember, when you have a point charge, PE is K Q1 Q2 over R. So this is if you have two charges, Q1 and Q2, separated by distance R. All right, the potential energy between these two charges is KQ1, Q2 over R. So how do you tell when you're going to use this one as opposed to the other one? Well, this one you remember is uniform. It's always going to be a uniform field. Now, what is the change in electric potential energy in a lightning bolt if 35 coulombs of charge, so I know immediately that at least 1Q is 35C, travels to the ground from a cloud 2 kilometers above, from a cloud 2 kilometers above the ground in the direction of the field. Okay, so what we're saying is it's moving with the field. So the E is going this way. So D is 2 kilometers, and we have to remember to convert this to meters. So this is 2,000 meters. Assume the electric field is uniform. So we have a uniform field and has a magnitude of E is 1.0 times 10 to the 6 newtons per coulomb. Now let's flip back. Which formula do you think we're going to want to use? The one for the point charge or the one for the uniform field? Well, of course, one for the uniform field. PE is minus QED. Let me erase that. So the potential energy, which is what we're looking for, is minus QED. The charge is 35 coulombs. And check this. Sometimes we will give you different charges besides just coulombs. We might give you a microcoulomb, which is 10 to the negative 6 coulombs. We might give you a picocoulomb. We tend to do that with farads, which is 10 to the negative 12 coulombs. Mostly microcoulombs in this class. So it's minus. All right, the charge is 35 coulombs. The electric field is 1.0 times 10 to the 6th newtons per coulomb. And the distance, and it says it travels in the direction of the field, so the distance is 2,000 meters. So this is going to be negative, multiply it out, and you get 7 times 10 to the 10th joules. Now, a point charge of 9 times 10 to the negative 9th coulombs is located at the origin. So I'm just going to go on and do my Q. Here it's sitting at the origin. A positive charge, so I know I'm going to have another charge, of 3 times 10 to the negative 9 coulombs is brought from infinity to a point such that the electric potential energy is 8.09 times 10 to the negative joules. How far apart are they? Well, clearly, this is a two-charge problem. So Q1 is 9 times 10 to the negative 9th coulombs, and it's at the origin, so this is the origin. Positive charge Q2 is 3 times 10 to the negative 9th coulombs. And the electric potential energy, so the potential energy electric, is 8.09 times 10 to the negative 7 joules. How far apart are they? Well, I know the potential energy electric is K Q1, Q2 divided by R. This is not squared this time. Let's solve this. R is K, Q1, Q2 divided by the potential energy. Now let's plug this in. K is 9 times 10 to the 9th. Q1 is 9 times 10 to the negative 9 coulombs. Q2 is 3 times 10 to the negative 9 coulombs. And the potential energy is 8.09 times 10 to the negative 7 joules. All right, multiply that out, multiply the numerator, then divide by the denominator, and you get 0.30 meters.